So now we shall derive an expression for the transition rate between two potential energy minima. We shall do it here for a one-dimensional model. This is a very simple model, but this will allow us to see the most important features of that derivation, and we shall also see how the rate depends on the potential energy barrier and the curvature of the potential energy surface near the minimum. These features will be also found in the consideration which we'll carry on later for a multidimensional potential energy surface. So this is a real simple example which will enable us to see all the essential features. The theory we're going to develop is called transition state theory. It assumes that if the system, being at the minimum, tries to overcome the potential energy barrier and find itself in another minimum, which could be shallower or maybe deeper than the initial one, is considered to be successful in doing that if it reached the top of the potential energy barrier, the saddle point or the transition state, with the velocity directed towards the final basin. Okay, the Hamiltonian of our system is given here, consists of the kinetic and the potential energy, and the canonical distribution then factorizes into two terms. So one is a spatial term corresponding to the potential energy u of x of our system, that x being the partition function, and p of v is the velocity term, essentially the Maxwell distribution. So this is our canonical distribution for our system being at that position, our one-dimensional system. The partition function is calculated over all span of x, but here we have to take account of only those values of the x where the system is at equilibrium, and this corresponds to the span from 0 to xb. xb is the point where we have the saddle point, and x0 is the point where we have the minimum, because this is the equilibrium distribution for the system being at equilibrium, so within the minimum. So probability to find our system with a particular velocity v at that point, at the saddle point, will be simply that expression calculated at x equal xb. The transition rate is a flux, and for the flux, number of particles going through a cross-section over unit time is basically equal to the velocity times the number of particles. So the number of particles is given by this, it's the canonical distribution times dv, because we would like to count for all the particles with the velocity between v and v plus dv. Then integrate over all favorable velocities. So the transition rate is given by this. This is a constant, doesn't depend on the velocity, can be taken out of the integral. So this is a spatial probability to find our system at the transition state. And v to the right is the average velocity calculated in that way. And look, when calculating it, we integrate over all velocities between 0 and infinity. So we explicitly state that velocities should be directed to the right. Only those contribute to the transition rate. That integration can be easily performed. First of all, we calculate the partition function, zv, first. Zv is given by this integral. It's a Gaussian integral. This is the result. Then this integral v times exponential is easily calculated by introducing a new variable equal to this exponent, and the final result after little calculation would be this one. Okay, now we need to calculate the potential energy part, p of xb. This is given by that expression at x equal xb. So first we need to calculate this partition function. So the partition function, the spatial contribution, would be given by that formula where we integrate from 0 and xb, as was said before, and we need to use u of x here. U of x is a general potential energy. It could have any mathematical form. However, because of this kind of parabolic shape of the potential energy surface, and we have a minus sign in the exponent, only values of the x around x naught, in the vicinity of x naught, would contribute most. And therefore, we can approximate the whole potential energy surface here by a parabola, which has a minimum at the point x naught. So this is what we do. We write u of x like this. So this is the value of the potential energy surface exactly at the minimum, plus a parabolic term. Of course, there is no linear term here because it's a proper minimum here around which we expand. So we substitute this u of x in our integral here, and this is what we get. This is a constant, and this is a Gaussian part. This expression goes to zero very quickly as x goes away from x naught in both directions. So these two limits here can be easily replaced by minus and plus infinity, in which case this is a Gaussian integral, can be easily calculated, and this is the result. Fine. Now we have all the ingredients, because our probability pi to find a particle at the top of the potential energy barrier would be 1 over zx, and zx is here, times an exponential at x equal xb. And the rate is given by that product. So we have v to the right, average, and the probability to be at the top of the barrier. So this is my v. This is z minus 1, zx minus 1, the one we just calculated. And this is the exponent for x equal xb. So now what we need to do is to simply multiply these things out, and you will find, after some cancellation, that transition rate appears to be given by that formula, where omega naught is that frequency, so which relates to the curvature of this potential energy well, and delta b is the difference of the energies at point xb and point x naught. So that difference. So we can see clearly that the rate, first of all, is proportional to this exponent. So the larger the barrier, the smaller the rate, exponentially smaller the rate. Also, we have this beta in front. So beta is 1 over kT. So the larger the temperature, the smaller the beta, and therefore exponential term is larger. So the larger temperatures, the rate should increase. So qualitatively correct result. Also, the rate is proportional to the frequency. This is also easy to understand. The more often the system oscillates inside the potential energy well, so the larger the omega naught, the more attempts the system makes to jump over the barrier, and therefore the rate will also increase.